morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. Today we are talking about compound events and tree diagrams. Compound events, more than one event, hence the word compound. Let's get to it, shall we? Suppose box X contains 2 blue and 2 green balls, and box Y contains 1 white and 3 red balls. A ball is randomly selected from each of the boxes. Determine the probability of getting a blue ball from X and a red ball from Y. So that's 2 different events, and we got to find that probability. We could find that using a diagram here. But there is a quicker method. Right here, there's 16 possible combinations, and the probability of getting a blue from X and a red from Y is 6 out of 16. But is there a quicker way to do it? Yes, there is. Okay. Events are independent if the occurrence of either of them does not affect the probability that the others occur. Drawing a ball out of this box, out of separate boxes, one draw does not, the draw out of the X box, the X box, does not affect the outcome of drawing a ball out of the Y box. So here we go. If A and B are independent events, then the probability of A and B occurring is equal to the product of their individual probabilities. And that is given right here, probability of independent events. Probability of A and B is equal to the probability of A times the probability of B. And that occurs even if there's more than 2 events. There could be 12 events, and you just find the product of each of their individual probabilities. Let's go. A coin and a die are tossed simultaneously. Determine the probability of getting a head and a 3 without using a grid. So we're looking for the probability of a head and a 3. These are independent events. Tossing the coin does not affect the result of rolling or tossing the die. So, what's the probability of tossing a head on a fair coin? Well, that's 1 out of 2. And what's the probability of tossing a die or tossing a 3 from a fair die? Well, that would be 1 out of 6. So the probability of both of those events occurring is equal to 1 out of 12. Yeah, that was easy. Okay, dependent events is where the first event does affect the result of the second event. For example, the best example is if everything, you have a box of marbles, and you draw one marble out of the box, and you do not put that marble back. Well, that affects the probability of drawing the second marble. In other words, the second event is dependent upon the result of the first event. The rule doesn't change, it's just the probability of A then B, or A followed by B, is equal to the probability of A multiplied the probability of B, given that the event A has occurred. Much easier to explain given an example. A box contains 4 red and 2 yellow tickets. 2 tickets are randomly selected from the box one by one without replacement, meaning I draw the ticket and I do not take the ticket back out. Find the probability that both are red. So we're going to find, let's see, probability of red, then red, okay, that equals, well, 4 red out of 6, so that is equal to 4 out of 6. Yes, you could simplify that to 2/3, whatever floats your boat, multiplied by, okay, so we're assuming this has occurred. Well, if I remove a red ticket and do not replace it, then I only have 5 tickets remaining. in the box. And also, one of the tickets are gone, so this 4 is changing to a 3. So that would be times 3 out of 5. Ka-pow, and I get, 4 over 2 is bang, 2, so 2 times 1/5 is 2/5. Of course, we could have gotten 4 out of 10 and then simplified that. But it's 2 out of 5. Okay. How about the first one is red and the second is yellow? Okay, so part B. So probability of red then yellow. Okay, so that would again be 4 out of 6 multiplied by, again, my total of tickets is 5, but the number of yellow tickets hasn't changed, so that's times 2 out of 5. So let's do some simplification. I suppose it would have been easier had I done it before, whatever. So that turns into 4 out of 15. That's the probability there. Okay, moving right along to another example. A hat contains 20 tickets numbered 1 through 20. If 3 tickets are drawn from the hat without replacement, determine the probability that they are all prime numbers. Oh, doctor! Let's first list the primes. Primes are numbers that have exactly two unique factors. Unique, in other words, they can't be the same. So 1 is out. It is not prime. That's the most common mistake because 1 does not have 2 unique whole number factors. The factors of 1 are 1 and 1, the same. So that it's out of the prime club. 1 is out. So my primes 2, 3, 5, 7, 11, 13, 17, and 19. Those are the primes. Okay, Prayer of St. Francis, very good. Videos on flash drive. Okay, so how many primes do I have in the first 20 numbers? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're going to draw 3 tickets. So the probability of prime, then prime, then prime is equal to, so I have 3 events, and they are dependent. So the first would be, there's 8 primes out of 20, so it's 8 out of 20, times, I am not replacing, okay, not without replacement, so that means my total goes to 19. And one of these primes has been drawn. I have to assume that. Doesn't matter which one. Let's say it's the 11. Gone. That means there's only 7 primes left. Okay. And now the third one. So now the total in the box, or in the hat, sorry, is 18. Another prime is gone. Doesn't matter which one. And I'm left with 6. And without simplifying that, I'm going to tell you that is equal to, oh, they just give me a decimal in the book, 0.0491. Okay, so that's a big nasty number. Approximately 0.0491 to 3 sig figs. Okay, I'm going to go ahead and stop and do part 2 with tree diagrams. Let's see how NXS is doing with Don't Change, and that will take us out of here. I am Mr. B. I've done all the damage I can do here. I am out! The sky above won't fall down. See no